Well, welcome back to another live stream by Electronics Pitara. And well, today's gonna be an epic day uh, as we get ready for James Webb Telescope. Oh shit! I mean, sorry for the live captions that are appearing. I'm gonna just change the language because I think the accent isn't matching well. So I'll just change it to United States and I like it. But is it back? Is back? Okay. So once again, welcome back to Electronics Pirata, and today, well, we're gonna be launching. Not we, but ESA is launching James Webb Telescope, and well, it's an exciting day. It's one of the biggest events around, and well, uh, as much as you are excited, am I am too, and like, everyone around the world is so much excited for this particular launch. So well, just need a little bit stretch. Okay, so before we get into the briefing, well, this launch is 2 hours away from what time it is. So we're 2 hours away from the launch to happen. So 2 hours. When you're saying, wait a minute, is it this big? So no, like for the first hour, for the first half an hour, 45 minutes, I'm gonna take up and just get it briefed. Then we can have some Q&A, and then we'll jump into NASA stream for some excited backend stories and way too much things to come up. Okay, so well, we are live on Facebook, Twitch, Twitter, YouTube. So there are many platforms to live on. Well, all those who joined from YouTube links are also there are links in the description for any other platforms you'd like to visit and watch up. So well, can I get some highs in chat? And well, this is a controversial question I'm gonna put in the polls. It can like just be getting heavy on me. Like I'll be asking, will it be possible for the James uh, to fail? Like, is it going to be success or fail? So well, we don't know much about this, so I'll just I'll not post it. I mean if I post it and something bad happens, I'll be held responsible by you guys. I don't know. Well, no more shit. So let's get into the launch briefing. And well, today's launch briefing is is a bit different than what we used to have, like all the images. While here, I'm gonna also get images plus, thanks to our everyday astronaut, well, we will also be able to see their website and go through their text for this briefing. So, so what are we waiting for? Um, are we waiting for? Yeah, we are waiting for, right? So launch stream be coming up here. Well, so this is James Webb Telescope here. So we'll go article wise and just I'll get it briefed here. We'll just change. Okay, perfect. Okay, perfect. So, as I mentioned, liftoff time is 12:20 UTC. That's the same as what's currently given to be 540 IST, and the mission name. Well, it's famous. I mean, James Webb Telescope. It's hyped up all over the internet, and well, who is the launch provider? Well, Ariane Space. It's an ESA's agency that handles usually all these big rockets, and it's usually held for private private sectors, when private sector is handling with the ESA, not the ESA internal launches but external contracts by the for the ESA is handled by Ariane Space. The launch providers are in space, and uh, who's paying for this? So it's led by NASA in collaboration with the European Space Agency, that's the ESA, the Canadian Space Agency, and the STSI, Space Telescope Science Institute, is also in this. So there are like 4 to 5 agencies who have combined to make such a big telescope. It's gonna be the biggest telescope, and it's the successor of Hubble Space Telescope. It's okay, so yeah, and it's gonna be launching on Ariane 5 ECA. Well, the ECA version is the bigger version, which handles two satellites at a time, two payloads at a time with a divider. There's a big structure, support structure between that the payload which has to be released first is placed on top. Then there's a support structure, and beneath it, that's closer to the rocket body, is the second payload which is to be released later. Well, I think this is probably due to the size, the bigger fairings and all are being used. Launch location is, as mentioned, from French Guiana in France, and it's its proximity to the equator. Yeah, people are mentioning its proximity to equator, but we'll just check it up at where's French Guiana. Okay, so French Guiana is not in. Okay, it's in Europe. No, okay, so it's not in Europe. As mentioned, it's in French territory, and it's actually on the this South America, Latin America area, in the Latin American continent here. So it's like near to Venezuela, Brazil. It's bordering Brazil. Yeah, it's in the border of Brazil, Suriname, Guyana, and near to Venezuela. So yeah, its proximity to equator is good, which means it can take the advantage of the high speed rotation of the Earth near the equator. So yeah, there is a speed difference, which I think we all learned in geography. Uh, Yeah. So what's the payload mass? Well, it's 6,500 kilograms, my bad. That's around 1400, 1400. Oh, sorry, 14,300 lbs. So yeah, that's why I think we'll be using the bigger ones, bigger rocket size. And where is the spacecraft going? Where it's going to the Lagrange point L2 between the Earth and Sun. Now, you might say, hey Aditya, what is Lagrange point? Well, we'll just get it clear here on what's the Lagrange point. Okay, so uh, where's this? So yeah, this is the Lagrange point, and this is the point where the sun and the other planets um, forces, okay, the centripetal and all these forces due to gravity are negligible, okay, they are neglected, they're balanced to each other, and I mean they're nullified here. So exactly at this point it's gonna be, so it's easy for this telescope to actually maintain an heliocentric orbit around the sun. So it gets easier for these space telescopes, and well, yeah, that's what it's about. Well, anyways, uh getting back to this one, getting back to this page. Well, I think we do not need to know if it's reusable, because there's only, I think, 1 or 2 agencies, Blue Origin and SpaceX, who are just have confirmed that reusability is a thing. The New Zealand based Star Labs, no, it's Rocket Labs. So Rocket Labs is trying to do, but it's in its testing phase. So yeah, it won't be recovering the first stage. It will crash there in the ocean, in the Atlantic Ocean, and no fairing recovery. yes, these fairings are new. And the weather, well, let's check the French. So here, ELA3 Guiana Space Center. We just gonna check here's weather. I don't think we do not need to mention the pad. I mean, if it's a big territory, big area, maybe we want to mention the launch pad for its particular weather. But I think this is a small. So yeah, well, it's cloudy. It's cloudy and there is humidity and precipitation. But because they're launching before 4 o'clock, we do not expect any 4 o'clock showers there. At least humidity stay because it's the equator area, which means they receive direct sunlight and all. And recently the winter solstice happened, so now it's gradually gonna increase the humidity and all. Well, so yeah, there are high chances. So what's the exact time we're gonna launching? 12:20, 9:20 there, which is probably somewhere between here. It's partly there. Okay, so yeah. Uh, well, there's slight chances of precipitation, and when there's slight chances of precipitation, I think yeah. So no, they're high. They're 54%. Okay, I was like checking here, but no. So we'll just uh, there are chances and there are high winds too. So not much high winds, like there are low winds. So maybe I mean it's good to go for launch type of thing. But yeah, there is a chance of scattered thunderstorm at 10 a.m., which probably does not shall not hinder here, but you can't say it's weather. Okay, it can change anytime unless you have a very high and good weatherman, highly qualified weatherman. So okay, this is all about the the first thing, first part, and well, these are just stats. 130th orbital launch of 2021, 289th Ariane space mission, 112th Ariane 5 mission. But coming back here, what does all of this mean? I mean, we'll be talking about this for the past 15-ish minutes uh, about the stats, but we don't know. I mean, what exactly is it? Okay, so well, we'll just get your things corrected. Um, okay, yes. So years. Yes. So what does all of this mean? Well, the James Webb Space Telescope will be launching atop of Ariane 5 rocket. So yeah, I'll show you what the Ariane 5 rocket looks like. Um, Quick transition, and yeah, this is how the Ariane 5 rocket looks. On the side are two boosters, two solid rocket boosters. In the middle is the Vulcan two rocket engine on its center stage. Well, it's pretty much resembles the Indian Space Agency's GSLV Mark III with its side two supporting side rocket boosters and two SRBs with a central engine, the Vikas engine what it has, but here it's the Vulcan 2 engine, and atop is another stage, second stage with a big fairing, and well, here's also a look on how the James Webb Telescope looks like. Okay, so yeah, here. So this is what the James Webb Telescope looks like. Um, It's pretty much it's a render. Okay, I mean not maybe not up to exact looks, but yeah, it's a pretty good render. It's not like I cannot say it's not up to the mark. It's way beyond the mark. Like it looks like a realistic render. I mean, yeah, the graphics industry has just reached heights. Okay, so yeah, not on these olden days where you used to have poor quality render. Well, sorry for that. Just a sore throat, and need more of water. Anyways, so getting back to our website. Yeah. So as I told you, James Webb Telescope on top of Ariane 5 rocket is gonna launch to the uh, Lagrange point 2, and it's and it will be succeeding the Hubble Space Telescope as I told earlier, and it's one of the NASA's flagship astrophysics mission. Okay, so its operational should be at least 5.5 years, but they are hopefully hope they are in a hope to stretching it up to 10 years. Okay, so that's just double. Okay, but yeah, I mean, when you see this to a car, I mean, you might think it's a bit on the impossible side, but when on these comes to space missions, well, these hardwares are so much tested and so much into put into effort that these go on to that double mission times, like the Mars orbiter mission of the India and many other missions. Like they just have elapsed double of what they were expected to work. One thing I think is that they either undervalue it so that it doesn't look like a waste of money, or like if they were to announce maybe 10 years and then it would just work 6 years, people might question the budget spent. But if you just use it the other way, it's like, I don't know if they're playing with human psychology, or is it truly that you evaluate correctly and then also it works 10 years. I mean, there's no idea. I'm not a professional worker there. Okay, so here's the James Webb Telescope. About James Webb Telescope, it's the largest space-based observatory ever built. So yeah, as I told you, it will be the largest built, succeeding Hubble Space Telescope. So previously it was Hubble Space, now it's like this one. So I mean, there are bigger observatories, but there's none in the space. Okay, so there's nothing in the space part. Okay, and okay, so there's nothing in the space part of it. And well, I just so yeah, I'm just checking some analytics. Okay, so hmm, what okay, so we just turned off captions. I mean, they were editing. Okay, so yeah, so it will be 100 times more powerful and will be built on 30 years of groundbreaking research. Okay, so I think 15 years after Hubble. So when did Hubble go? Okay, launch. So yeah, it was launched in 1990, and as just around that time, it was declared that we are going to build a, uh, another satellite to another telescope to succeed it. But I think till 7 years there wasn't any work, and after which it had a pretty much delayed, and here again delayed. But for now, it was 30 years groundbreaking research from 1990 to 2021. That's the around time. Hubble is okay. It's still there. So Hubble's working, and that's all the research data we have. Okay. So while the JWST is based on infrared wavelengths, and compared to Hubble, which was for normal and UV lights, and it will be providing images and research. Okay, so it has research equipment as well as mirrors for the images. So its four primary goals: it has to examine the first light in the universe and the object that formed shortly after the Big Bang. So yeah, I'll explain these points down in detail like as we scroll down. But for now, you can see, as suppose this is the first light of universe, and we are supposedly here. So this much, this length is around 13.8 light years. So it would be taking 13.8 billion light years. That's, I mean, if you think this is 13.8 billion light years, and it would take 13.8 billion light years, that's 13.8 billion years. Okay, because light travels at the speed of light. I mean, whatever speed. Okay. So this is 13.8 billion light years away. So it would be taking 13.8 billion years to reach, for that light to reach here. Okay, and now supposedly, if we put a telescope here now, we would be seeing those first lights, because we are 13.8 billion years into the time. Okay, so we are into that time, and now these lights are reaching, and if you put a telescope and any sort of imaging thing there, you'll be able to see those lights now. Okay, so that is what, and maybe around that time, those big bangs things, all those lights are now reaching us. Okay, and the second point is to investigate how galaxies form and develop. So yeah, it's to see, uh, it's to investigate how these galaxies are forming. And thirdly, to observe the formation of stars in planetary systems. So nearby nebulas and all, uh, these can be also imaged to show the formation of stars and planetary systems. Okay, and look at the physical and chemical properties of a planetary system and investigate the potential for life in these systems. So maybe there's some solar system nearby, the planetary system nearby. So these lights coming from them, infrared lights and all that, can be examined to get the chemical and physical properties contained in these lights. As we see them, and investigate the potential for life. Okay, so maybe hydrogen and water has some particular, some particular chemical property and physical property to the light infrared spectrum, or maybe it's the infrared spectrum that's bringing those lights, and we can just possibly see them to take the potential for life on these systems. Okay, on these planetary systems. While coming to what was one of these biggest hypes of these mission. I mean, why this mission has been hyped up is because its development almost took 30 years, like 7ish years for the official development, and then different. So yeah, it's said to be delayed by around 15 years from its original launch date, and 15 years was the initial build time from its announcement. 7 years in the official work to start, 8 years for an expected date. Hello reboot level. If you're gonna spam, I mean, I'm just gonna I'm just gonna put you on timeout. Okay. I mean, I didn't put a night bot today. Okay. I haven't been putting one since a few days. I mean, a few streams, because it's just gonna irritate you guys. Okay. So just let it be. Okay. Last one. Anyways, coming back to the point. Uh, what's the status of the reboot 11? You just broke my continuation. Okay. Anyways, so we have 25 minutes before NASA gets into this play. So yeah, we have to bit hurry up. Okay. So anyways, telescope began in 1989, but as I said, 7 years for official development to start. So first it was Next Generation Space Telescope, but in 2002 it was named JWST, James Webb Telescope, Space Telescope, and it was planned to be an 8 meter aperture located L2 and with the cost of $500 million. But at this time the telescope was initially launched in 2007, as I told you. But it's subject to 16 launch delays, cost overruns, and major redesigns. The original design and the new design would have a vast difference. In 2004, the construction actually began. I mean, 1969 paper designs and 8ish years before you could just get these structures and all things ready. I mean, started 2005 Ariane 5, and the location was chosen. Over the decade, individual spacecraft were built, tested, and 2016, by November 2016, final construction was finished and testing could begin. Like all those testings after assembly, one more test. In many tests were many tests are to be held, and but it was delayed in March 2018. Okay, to 2018 because one of its sun shields had one of its huge sun shield had ripped during a test, and when they reviewed it, it had 344 potential single point failures. Like any one of these could make the entire entire structure stop working. So like these are huge amounts. I mean, you don't want even one of them to be in your space projects, because I mean, the once it's gone. Okay, and it stops working. All that money is in drain. It's just a piece of garbage then, until you could get something out of it, but still majority it's garbage now if you have even one point potential single point failures. So yeah, it was again construction happened, all these points were removed and all that thing happened, and well, it arrived at 12 October, and it had been started to integrate on the rocket. So they had folded it, and they were getting it into the fairings on the rocket, when on November 22nd, a clamp band, which secured it to the payload adapter, had accidentally released. So it caused the telescope to vibrate. Okay, vibrate a bit. So they had to again check, and well, another month, and it was to be yesterday the launch, but due to weather, it's not today. So yeah, well, I think it's on the pad now, and now, well, why was it renamed? Okay, I mean, one could have said Next Generation Space Telescope is a good name. So James Webb Telescope was uh, the name of James Webb was the name of the second administrator of NASA, and he's best known for heading up the Apollo program. And so in his dedication, uh, so yeah, in his dedication, they named it, uh, recently, Webb had uh, was alleged in some LGBTQ discriminations, which uh, which uh, which led to many people urging NASA to rename him, but they said no. They said like we'd not name it, and we do denounce. I mean, they did not accept those claims of his discrimination for the community. Anyways, so getting to the working. Well, it has four elements: the spacecraft bus, the integrated science modules, the optical telescope element and the sun shield. Okay, so here's the optical element. I think um, okay. So yeah, so this is the science module. These are the flaps to stabilize it, solar power, earth pointing antennas. Here's the bus for all of these machines, including computers and etc. Here, in the science module, there are mostly cameras and science instruments. Okay, star tracker for patterns of the star patterns to target the observatory, and this is the multi-layer sun shield for the instruments to be protected, and these are the primary and the secondary mirrors. Now the primary mirror is coated with gold, only like not a very thick layer of gold, but yeah, it has around 8 to 9 people pure gold rings. uh, uh, I mean that much amount of gold is there, okay, on 18 hexagonal segments, like in total. Scrolling down, this is the spacecraft bus. Weighs about 350 kilograms, and it's operating at around 27 degrees Celsius, 80 degrees Fahrenheit, and on the SI units, 300 kelvins. The bus also has 6 reaction wheels. Now you might be thinking, what are 6 reaction wheels? Well, I'll let you know. Uh-oh. Yeah. So 6 reaction wheels are these small wheels which will rotate to produce a torque. Okay, so they'll rotate in such a way like drone motors do. Okay. Here. So these motors, uh, like these wheels will rotate and produce a torque. Okay. They produce a torque which helps to rotate. Uh, I mean, rotate and change position of the telescope. Okay, so that's the reaction wheels. Anyways, so there are two star trackers, as I told. These they'll track the stars and all, so as to point where to point them, and get the correct images and all. It also holds the propulsion system. There are 10 pairs of thrusters, each having one primary and one backup thrusters. They use hydrogen for fuel and dinitrogen tetroxide for oxygen oxidizers. So yeah, fuel needs oxygen to burn and combust, but in space there's no oxygen, so we usually carry oxidizers. Okay, and yeah, that's about that. The sun shield is needs it. So yeah, the telescope actually needs to be under 50 Kelvin. Okay, that's minus 223.2 degrees Celsius, minus 369.7 Fahrenheit. So uh, yeah, if it is hotter than this, the telescope's own infrared radiation would stop the instruments working correctly, because it works on infrared, like it captures infrared lights, and so it might hamper the working of these instruments. So yeah, this how big this sun shield is, and I think I'll have a photo of here, the sun shield. Okay, we don't have, because we particularly have 10 here. So, anyways, uh, just let me check. Okay, all of a sudden, if yeah, we have 15-16 minutes. So, anyways, getting back to our optical elements of the telescope. So yeah, this is the primary mirror and the secondary mirror. The gold plating is only 1,000 atoms thick here, and it will optimize the reflectivity in the infrared spectrum. Okay, so the infrared spectrum reflectivity can be optimized by these gold platings, and these are 6.5-meter diameter mirrors, and there are like 18 of them. And there's also secondary mirror which is here. Okay, so this is a small mirror. Usually I think it's the size of the human, or maybe the just the human abdomen. But this is huge. Well, there are integrated science modules, each having different uses. So this is the NIRCam, the near infrared camera. So this is an infrared imager. So it will be used for imaging purposes, uh, and it can see from 0.6 micrometers to 5 micrometer spectrum, and this has 10 sensors, each 4 megapixels. Uh, then there we have near spec. So it's used for spectrography of the same wavelength as of the NIRCam. And so yeah, I mean, I don't have any idea for spectroscopy, but yeah, we'll just get that thing also clear. I mean, what are we here for? So spectroscopy is the study of interaction between matter. So yeah, so like these waves coming and the matter. So what's the study of this interaction? Okay, because light is a wavelength. It's an electromagnetic spectrum. So the interaction of this when it's studied is called spectroscopy. Okay, I mean, I don't have great knowledge in this. I mean, not not a complete physics person. Okay, getting to my right. So these were the near infrared. This is the mid infrared, and it is a bigger wavelength for bigger. Uh, uh, I mean, the more thicker wavelengths, like from 5 to 27 micrometers, and uh, well, yeah, that's also for imaging. And we have a last one, fine guidance sensor, and that's near red infrared and near infrared imager and slight less spectrograph. So it will obviously for fine guidance it's for the stabilization of the observatory's line of sight. So yeah, when we photograph, our hands also might shake, so it's for its stability. Uh, and well, the others are spectrography for 0.8 to 5 micrometers of wavelength. So yeah, that's all about that. Well, I'll just show you some images for it. I mean, okay. So transitioning to this on stream. This is the NIRCam. Okay, so yeah, the highlighted part is the NIRCam, NRI cam. Sorry, this is the NIRSpec. I mean, maybe I have written down this means NRI spec. Yeah, it's near infrared. So yeah, I mean, my bad. It's NIR cam and NIR spec. This is the mid infrared range in imaging camera and sensor, and yeah, and this is the stabilization and another spectrography thing. Okay, yeah, this is the full infographic that we showed earlier. uh, so yeah, that's about that. While moving on to its deployment timeline, uh, so yeah, at t minus 0 it launches. At t plus 3.2 minutes it's fairing separation. T plus 30 minutes it's separation from the launch vehicle, after which it's the NASA and it's the telescope team's responsibility to handle what's going on. Then there's solar array deployment, sunshield deployment, arena deploy, antenna deployment, sunshield deployment. Then there will be some burns, and well, here's a full deployment thing. Okay, so here's it's waiting for launch on the launch pad. Here it is launching. Yeah, so now from here it's the main part. So from here it separates from the launch vehicle's upper stage, which I think is too small compared to what the lower stages are. I mean, it's very small. So here we have the solar array deploying. Okay, then we have the first mid-course correction burn. So yeah, this is something important what I'm going to explain here. Okay, so uh, suppose if the you might think why correction one. So suppose if Ariane 5 was to put it on its full thrust and send it. Okay, so in case there would be, okay, so it's atmosphere, and physics has these exceptions and all too. So in case it's oversped, okay, so it cannot turn behind and slow down, because that would heat up all the instruments, okay, because it would turn back. And you might think then just put on the heat shield, a sun shield, but that's not the solution, right? Because some parts have to be exposed, and some parts it adds to the weight and all. So yeah, so they are gonna speed it up, slow it down, so all that things, those angles and all, that's gonna do. So yeah, the iron fly is gonna underburn, and then it will let this thing do its work. Anyways, getting back to our yeah, yeah. So then there will be these antennas which can gimbal, so it can gimbal around the point. Will be deploying. Then they're going to be, okay. Then there's going to be another burn. Uh, then there will be the forward sun shield palette will deploy, and then yeah, exactly, this after sun shield palette. That's the palette because the sun shield is rolled in with a protective covering. Okay, then there's going to be a deployable tower assembly deployment. I cannot see that here. Maybe it's hidden somewhere or what, I don't know. So yeah, after which there's going to be another deployment for half momentum flat. See, this is also an uh, you know this will also help for momentum to minimize fuel usage during the mission. After deployment, these will give the momentum. uh, then yeah, the sun shield cover is released. So as I told you, those pink membranes that were on it are released. Then we have the mid boom, which is the deployment step for this part of the sun shield, which gets expanded. Then there's on the other side, so yeah, starboard and sunshield port. I mean there are two names for it. Then they're tensioning it, okay. So it's to this maximum, to stretching it and perfectly tensioning it so it doesn't go loose. And this is the confirmation that yeah, it has completed tensioning. Then the secondary mirror will deploy, it will start its deployment. And yeah, this is the abdomen sized case that's deployed here, abdomen sized mirror deployed. Then radiators and instrument radiators will deploy from the back. Then primary wing of the port primary wing will start deploying, and it will look something like this. Okay, so it's half folded. Then the second starboard primary wing will start deploying, and it will look somehow like this at the end. So yeah, this shows that it's completely deployed. So Webb is fully deployed now. And post that, individual mirror segment will start moving to check and all. Is The movements are completed. This is around 15 to 24 days after launch. Okay, so yeah, it's not a small. Okay, then there will be final insertion burn. That's another mid-course correction burn. And finally, Web 2 is orbiting in a hollow orbit. Well, this can be also accessed at this link, which I'll be putting down in chat. Or I just put it from here. Good. So yeah, I think everyone's online and people are watching. Okay, coming back to this orbit. Well, I told you what's or a Lagrange point. It's where the centripetal forces balance out needed for spacecraft to move with them. So yeah, both. like two large bodies orbiting. The gravity balances out the centripetal forces needed for such spacecrafts to move with them, which means it needs very little fuel to keep it in a desired orbit. Okay, so I mean, this is how they save on fuel, like reaction wheels, momentum flaps, Lagrange points. So yeah, and its observatory's hello orbit is around 800,000 kilometers, has a radius, and it will take half a year to complete. So yeah, it's a diameter of around 1.6 million kilometers, and it's around 1.5 million kilometers away from the Earth. Okay, so yeah, it's this far. Okay, and it's behind the Earth from the position of the Sun. So yeah, that's how. Well, this is a lot to understand, but yeah. Uh, so as I told you, it will be able to see 13.6 billion years light away from this much, and it will be also it's observing the infrared spectrum because of cosmological redshift. Because in during redshift, lights appear to be redder in wavelength, and it's near the infrared spectrum. Uh, and it has JWST has been designed to see ultraviolet light that has redshifted into infrared. Okay, it can distinguish which is originally infrared and which is redshifted to infrared. And well, it's because it's a successor. Because uh, is also to key seeing further than previous telescope because of cosmological redshifts, as I told you, because of infrared can uh, as we move to infrared spectrum, more of these lights from farther distance can be seen due to the redshift phenomenon. And why do we need this particular? Because infrared bands need around minus 232 233.2 degrees Celsius to be seen, whereas Hubble is at 15 degrees Celsius. So yeah, I mean the you need to be at a chiller temperature, and where there's cosmic dust which scatters visible light, infrared observations can still be made. And yeah, here's the difference between visible light and infrared light. Okay, so yeah, that's why. And well, there's a lot of this to be understood, but I mean, they're out of it. Yeah, this much what needs to be understood. And by this is the RN5 ECA, as I told you, of its capability to launch two big payloads. This is the main stage with the Vulcan 2 engine. This is the second stage. This is also cryogenic stage, and obviously this will be a cryogenic stage too. But this is particularly made, okay, by Egypt. I mean, them themselves. Okay, this is developed by them. Okay, that's all for launch briefing. RN right now. Okay, so uh, let's see what's the status of NASA. Okay, so NASA has started it in its launch broadcast. So we'll just transition there. Well, it is about this, okay? So, well, I just gonna update my schedule.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We've crossed the solar system and sent ships to the stars. But we continue to search. We can't help it. A central element of the human future lies far beyond the Earth. If we crave some cosmic purpose, then let us find ourselves a worthy goal.
You're looking at live footage of an Ariane 5 rocket in Kourou, French Guiana. At the very top of that extraordinary machine, one of the largest rockets in the world, we find the most ambitious space observatory ever built, the James Webb Space Telescope. And today is launch day. From all of the people all around the world working on today's launch, good morning, bonjour, buenos dias. This is live coverage of the historic launch of the James Webb Space Telescope. I'm Michelle Thaler, speaking to you from NASA's Goddard Space Flight Center in Greenbelt, Maryland. And I am very excited to be with you today. Today, the James Webb Space Telescope begins its journey to explore the edge of our observable universe, and its journey into history as well. This launch has been years in the making, and the world has turned out to watch. We'll have a lot to discuss both before and after launch, but let me set the scene for what's going on around us. While I'll be anchoring coverage from here at NASA Goddard, the big stuff happens today here at the Centre Spatial Guyanais, the Guiana Space Centre in French Guiana. This is the main launch site for the European Space Agency, a close partner in this once-in-a-generation mission, and the home of all Ariane launches. Katie Haswell is there at the launch facility and joins me now live via satellite. Okay, how are things in Kourou, Katie?
Michelle, things are looking really good. The boards are green, the mission controllers are focusing hard, we are go for launch. We've had our eye on the weather the last couple of days. The weather's been a little bit inclement, so we're keeping an eye on that, but otherwise everything's looking absolutely great. And I have to tell you, there is just such a buzz of excitement here in the Mission Control Center. It's a remarkable feeling. Right now we're topping
different ways, but one of the main ways is actually using the transit technique. And this is an indirect method where we actually detect the decrease in starlight that happens as a planet goes in front of its star. But then imagine the planet has an atmosphere where, well, there's an additional decrease in the starlight because the atmosphere blocks the light as the planet goes in front of its star. And why it blocks the light is because there's usually a molecule or something in there, like water and methane, like I mentioned, that is acting as an absorber and blocking the light from our telescope, in this case, Webb.
So going from, the relatively nearby stars and planets, Macarena, you're an expert on very distant things, distant galaxies. So how does infrared contribute to your field of study?
So with Webb, we're going to be able to observe the very first galaxies in the stars. We're talking about 3.5 billion years ago, so it's really mind-blowing if you think about it. And why infrared? Well, those galaxies emitted their visible light many, many millions of years ago, and that light travels towards us in time, and at the same time, the universe expands. So in that process of travel and expansion, the light shifted from the visible to the infrared, and so Webb will be able to actually observe those very original primeval galaxies. And not only those, but it will also allow us to observe everything in between, so we can understand the evolution of our galaxies from the first ones to the ones we see today.
This is something kind of amazing. So our eyes interpret different energies of light as different colors. And infrared light is a color that our eyes are not sensitive to. But like you said, it's actually just the space of the universe stretching out the light and changing it from visible light into infrared.
Into infrared, exactly.
So how are these first galaxies different from galaxies today?
Well, when you look at the images we have of the oldest galaxies we've seen, they look like fluffier and clumpier. We know they have a lot of star formation, so they are actually, that's a really good signature to measure them. And they are like little seeds that afterwards they merged and got together and evolved until the ones we see today, which are like spirals and elliptical galaxies.
So from the near universe to the far, one of the things that infrared is very good is seeing through dust. That's another huge advantage. Maybe Nicole, could you sort of take us through that story?
Sure. With dust, first there's a lot of dust in the universe, but how stars and planets form in the first place, they are forming in these very dense clouds of gas and dust that come together, and it's very difficult to see through them with normal visible light. And so the infrared is actually able to see through that, almost like an X-ray, sees your bones, sees through our skin. You can use a telescope like Webb to see through the dust and see the inner stars forming, or see some newly formed planets that are also very warm from having just formed.
And there's even a possibility of seeing some of the very first stars, or at least some evidence of the first stars that might have existed. But could you tell us a little bit about that, Macarena?
Yeah, so the very first stars, they form right around the time of the very first galaxies, even before that. And so we'll be able to measure them, maybe not the very first one, but the first population of the stars, which is really interesting because they were formed out of a very pristine material. And then from there, they evolved into more evolved stars that created all the elements we know today, things like gold, platinum, carbon, everything. Us were formed out of those original stars. So it's a really amazing adventure to observe all these objects and understand them better.
There's so many wonders in the universe, and one of the things that I would never have believed was real unless I'd seen the data with my own eyes, is the TRAPPIST-1 system. And that this is actually going to be one of the targets for Webb, is that right? Tell us a little bit about TRAPPIST.
Sure. TRAPPIST-1 is, like you said, it's going to be a target. There's 7 planets in the system, and they're all small, around the size of Earth, actually. So it's also a very compact system. So it's not just that there's a lot of planets and that Webb's going to observe every single one of them, but it's the compact nature that's just really fascinating, because the entire orbit of the planetary systems, like all 7 planets, they fit inside our orbit of Mercury around the sun, and Mercury is our closest planet to the sun. So imagine 7 planets in there, and there's a lot going on, but it's very exciting because we'll get to learn and do comparative science and see, are all these planets, do they have the same chemical signatures in their atmosphere? Do they all have same amount of water, carbon dioxide, things like that?
Well, thank you so much. We're going to be back to talk to you more, but thank you for joining me.
Thank you.
Thank you. Okay. So we'll be back in some more minutes to talk with them. And remember that we're taking your questions, so use the hashtag AskNASA. Webb looks like nothing that's come before because it's pursuing scientific goals like none that have come before. It's taken years to prepare it for flight, and as you might imagine, plans of this scope and scale inevitably run into unexpected challenges. Along the way, just like any of us, it encountered things like snowstorms in the east, wildfires in California, hurricanes that deluged Houston, Texas, and of course the global COVID-19 pandemic, which added its own profound challenges to the whole team. This story really warrants a recap, so check this out.
The Webb Space Telescope presented many engineering challenges, but engineering hasn't been the only obstacle the team had to overcome. In 2011, an outbreak of tornadoes cut electricity to the Marshall Space Flight Center in Alabama for nearly a week, while the team rushed to finish cryogenic testing on the primary mirror segments using power from diesel generators. Engineers had to endure a large snowstorm, known locally as Snowmageddon, while testing the Integrated Science Instrument Module at the Goddard Space Flight Center. And of course, everyone has had to contend with the global pandemic. One particularly memorable challenge was working through Hurricane Harvey in 2017. This massive cyclone dumped 40 to 60 inches of rain across the Houston area over a 4-day period, causing catastrophic flooding and $125 billion of damage, all while the telescope was undergoing cryogenic testing at NASA's Johnson Space Center. Though the telescope remained safe inside the test chamber, water leaked through the ceilings, people had to cover workstations in plastic tarps, food was in short supply, and a few team members trapped by floodwaters had to be rescued by boat. It was rough, to say the least, but the team and the telescope survived the storm. Despite winds and snow and endless rain, the team got it done, and Webb is now ready for its final journey atop a rocket into space.
While the Webb Telescope is a technological marvel, everything here began with questions. Questions about how the first stars and galaxies came to be. Questions about whether planets around other stars might have environments that can sustain life. And of course, the promise of discoveries we can't even predict yet. A few days ago, I had a chance to speak with someone who's probably the best person on Earth to help us understand what we know, what we don't know, and how Webb will help fill in those gaps. Dr. John Mather is a Nobel Prize winner who measured the Big Bang with an observatory built here at NASA Goddard. John is Webb's senior project scientist, and we're so pleased to have you here today, John.
Good to be here with you, Michelle.
So to start this incredible story of Webb, let's start with something that's deceptively simple, gravity. There's something special about gravity.
Gravity is special. Gravity always pulls. It's the only force of nature that always pulls. So that's special. And what makes that special is that gravity, although it's very weak, is very long range. It can reach across the universe and slow down the expansion of the material that came from the Big Bang, turn it around, pull it back together, turn it into galaxies and stars, and eventually planets and a place where we could live. So that's what makes gravity special among all the forces of nature.
And something so simple, like just the idea that it's always pulling together, that simplicity leads to wonderful complexity, doesn't it?
Yes, because it's always pulling, it's possible for gravitational energy to be converted into kinetic energy, just heat, and the universe becomes self-heating, which is not something the other forces could do all by themselves. Clouds of gas can be compressed by the gravity until they get big enough and hot enough to light up and have the nuclear reactions inside that turn hydrogen and helium into the chemical elements you see around you, here in the house, here on the set. So carbon, oxygen, nitrogen, everything we have that we think of as ordinary came from inside stars. So we are stardust, as Carl Sagan told us, but there wasn't any stardust in the Big Bang. So we need this part of the story to be figured out. How did we come to be able to live here on our little planet when the universe started out without all of these goody things?
So you mentioned these planets around other stars. So we're almost sort of going through all these amazing science goals of the Webb. What can Webb tell us about planets around other stars?
Well, once in a while, a planet goes in front of the star, and some of the starlight goes through the atmosphere of the planet, if it has an atmosphere, on its way to the telescope. We will spread out that light into a spectrum, or what you would call a rainbow, and we'll analyze it to see what are the chemicals that are in that atmosphere. So we will be able to tell you that maybe, that's the plan, whether those little planets that might be like Earth actually could have, for instance, water in their atmosphere, and maybe enough water so there could be a liquid ocean under that atmosphere. One of the great questions. So we know they're planets. We know when we should look. We just don't know what we're going to see.
So after the Webb launches, one of my dreams is I'm going to be standing outside in my backyard and point to a star and say there's a planet around that star that we know has water vapor, oxygen, perhaps methane, carbon dioxide. So what is Webb going to also do in the search for life closer to home, our own backyard?
Well, here in our own solar system, we will be looking at everything from Mars on outwards to the farthest we can see. Satellites, comets, asteroids, and the planets themselves. And some of them are really interesting and special because we know they're possible homes of life. What would make a thing a home of life? Well, if it's wet. That's a good clue. So the satellite Europa, which orbits around Jupiter, was discovered by Galileo himself. And we know now that it has an ocean that's covered with ice. There are cracks in the ice where water comes spitting out. NASA are going to send a probe over there to fly through those plumes. We're also going to point over there with the Webb Telescope to see what can see about that atmosphere and those plumes of water. We'll be looking at Titan, which is a satellite of Saturn, which is so big that it has an atmosphere enough to fly a helicopter. And it is cold out there, so that what they have, what is on the surface, is solid ice. And over that are liquid hydrocarbons, which you would use for fuel here in our home. But over there, it's liquid rain, lakes and rivers, and we will be looking at the geology of that before we send the helicopter out there.
So you're on this amazing journey from the very distant early universe all the way to our own solar system, but there's also been a personal journey for you. You've been working on Webb since the very beginning of the mission, is that correct?
I have since '95. We had our first conversation, but people were even dreaming and imagining way before that what we needed. And you could tell even before we launched the Hubble what were the possibilities, and we learned that we would need an infrared telescope that could do things that the Hubble could not do.
Well, John, I've been an admirer of yours for many decades now, and it's an honor to be with you on this part of the mission. So thank you so much for joining us. Best of luck on the launch and the mission ahead.
And thank you for asking all these great questions.
The Hubble Space Telescope delivered profound insights about our place in the cosmos. But perhaps the biggest takeaway from Hubble is that we've only just scratched the surface. Hubble gave us the best ever views of stars and planets forming inside vast, dark clouds of dust. But as soon as we had that data, we were asking new questions that needed better measurements, clearer images. Hubble was also able to capture images from galaxies so far away. Their light took 13 billion years to travel to us. These distant galaxies are just tiny dots in Hubble's images, tantalizing scientists with clues about how the first galaxies formed. In order to pursue a better understanding about the earliest days of the universe, we needed to build a better time machine, and that's Webb. So I'm going to be rejoined here by Nicole and Macarena, and this is our chance to talk a bit about building that better time machine. You know, what about the technology of Webb? So there's so many aspects of Webb to start off with, but maybe again, going back to the theme of infrared. The design of this telescope is so different because we had to use infrared light, heat light. So tell us about some of the challenges of, for example, why does it have to be so cool? Tell us about infrared light and the design.
Right. Well, I think we've heard already just how cool it has to be. It's around or below 50 Kelvin, and that's minus 370 degrees Fahrenheit. Actually, below that is what it operates at, and that's very cold. And the reason we need it so cool is because we don't want the telescope itself to detect itself, because there's several instruments on board. There's 4 different instruments, and there's some moving parts, and so you need things to be cool because you want to detect these faint signatures from either an exoplanet atmosphere or faint light from the earliest stars and galaxies. So you just don't want to detect your own telescope.
Now, Macarena, you are the instrument calibration scientist for the coolest instrument.
It is the coolest
on Webb.
Yes.
MIRI. So tell us a bit about MIRI and why it needs to be so cold.
So MIRI, it's a really unique instrument, and it's a great example of this collaboration we have in this mission because it's half European, half US. And so MIRI is the only instrument on board that uses the mid-infrared light. And the mid-infrared light is a bit redder, a bit cooler than the near-infrared light, and so because of that, MIRI needs to be colder in order to detect that very faint signal from high-redshift galaxies or protoplanetary disks, etc. So because of that, it's the only instrument on board that has a cryocooler. So it is not only the passive cooling from the sun shield, it is active cooling, and it brings it down to about minus 450 Fahrenheit. So it's really extremely cold, a few degrees above the absolute zero.
And we were talking about you don't want the telescope to be so hot that it's basically giving off its own signal, its own radiation, and that leads us to why it needs to be in space, right? So tell us a bit about why do we need to launch this thing into space to see these wavelengths?
Well, again, it kind of goes back to atmospheres because Earth has an atmosphere and there's water in Earth's atmosphere as one example. I mean, there's a lot of other molecules, but basically in the infrared, at the wavelengths that we want to observe some of these stars and planets and galaxies, those wavelengths are actually where Earth's atmosphere is opaque. So with telescopes located on Earth, even at higher mountains where they try to get above the clouds or atmospheres sometimes, there's still residual atmosphere that we're trying to look through and peer through. So in order to see the full infrared wavelength range at a very high sensitivity as well, we need to go to space.
Absolutely. So we talked a bit about some of the power of techniques like spectroscopy. We've heard Dr. John Mather talk about it. So let's go a little bit more into the details of how spectroscopy works and why it's so powerful.
Oh, sure, yeah, I can keep going. You know, well, with spectroscopy, we heard, so visible light, again, is kind of, it's a rainbow of colors that we don't see naturally. But if you use something like a prism, you can separate out that light and see all the colors from, you know, blue to red. But then the infrared is redder than the human eyes can see. But you can still do the same technique where you have spectroscopy tools or instruments like Webb has, all these spectroscopic tools, so that we can break up the infrared light and look at certain colors, if you will, so that we can see certain features that we are looking for, whether it's the right wavelength where, you know, a galaxy might be bright or where water is absorbing in an atmosphere.
So, Macarena, MIRI has many different capabilities.
It does.
And in fact, it has one that I believe is something different called coronography as well.
Yes.
Tell us a bit about all these ways that we're going to detect, you know, different signatures from planets.
So coronography, it's an amazing technique, but essentially it simulates an eclipse. So when we have a very bright star with planets around, for instance, usually when you take an image, the stars outshines the light of the planet, so you don't see them. But with MIRI and with other instruments, NIRCam as well, you can actually block the light of the star and dim it, and then you see the planets around. And it's really a technique that's going to be very much used and to do, like in this image, direct imaging of planets.
Well, thank you so much. We'll be back to talk to you more with some social media questions. Thank you very much.
Thank you.
NASA and its partners began developing the Webb Telescope years ago, growing from an initial inspiration to a design, then schematics, and finally, reality. What started as a big dream for studying the origins of the universe required best-in-class engineering expertise to transform into something real. Let's take a short look at the very long story about the earliest days of the James Webb Space Telescope.
Before the Hubble Space Telescope even launched, scientists were already discussing what should come next. Ideas for what was then called the Next Generation Space Telescope evolved throughout the 1990s, and by the end of the decade, NASA had a preliminary plan. Construction of the James Webb Space Telescope began in 2004. Beryllium was mined to create the mirror segments, which technicians polished and coated in a thin layer of gold. Meanwhile, engineers designed and built new science instruments in the US, Europe, and Canada. Every step of the way, there were reviews and tests to make sure each part could withstand the rigors of spaceflight. By the early 2010s, the team began bringing individual components together at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It was there that the mirrors and instruments began to coalesce into the grand machine we see today.
We've said before that the James Webb Space Telescope is an incredibly ambitious mission. Big ambitions come with big challenges, and that's certainly been the story of Webb. From the beginning, the design of this observatory has been a balance between the boldest questions scientists have dared to ask and the cutting-edge technology that our best engineers could offer. The design for Webb evolved from earlier ideas of what a telescope could be, another example of the delicate balance between desire versus capability. To get a better understanding not only of the mission's goals, but also the mechanical guts of the observatory itself, I recently got a chance to speak with a pair of engineers who know the anatomy of the Webb telescope better than just about anyone. I'm here with Keith Parrish, a senior engineer on the Webb mission. And Keith, you brought something to show us today.
Yeah, yes I did. So conceptually, Webb Sunshield is actually quite simple. All we need is 5 tennis court size pieces of this material outstretched to protect the telescope from the sun. So what I have here is an actual sample of that material. This is just Kapton. It's
so light,
yeah, it's an industrial, you can buy this, and on, you know, it's commonly used. And what we do is we buy it for Webb. We seam it all together in small pieces, and then we actually coat it with special coatings to give it the what we call the thermal properties we need in orbit. So this one has a nice pink or purplish kind of hue to it, and the reason it's purplish in hue, we use this on the sun side, and we actually put a silicon material on this Kapton, and then we actually put a little bit of a metal in it, and what that metal does is it gives us a nice electrical conductivity. We don't want any surface charging building up, and the other thing is this silicon coating actually drops the temperature of this layer. So, and also it's very durable and can survive, you know, for many, many years in space.
And then this whole thing has to unfold somehow. Where we can actually see that behind us.
Exactly right. So if you look at that animation there, unfolding there, so it's actually S-folded up, almost like a fan. We call it S-folding. And once we get it all folded up, we secure it to a structure by actually pinning it for launch. So, you know, a huge shout out to our mechanical engineer and our entire Sunshield team, because they've come up with some really clever ways to secure this for launch, unfold it, fold it, and then, you know, ultimately get it safely deployed in orbit.
That's wonderful. So speaking of unfolding and all these pins that need to release, let's go over here and talk to James Cooper. You're going to show us what's going on there.
Yes, hi. So I have here an example of a non-explosive actuator. We have 178 of these.
These are all these little pins we're talking about, right?
James Webb, right.
Yeah.
107 of the 178 are the membrane release devices. And we use this type of actuator because it produces a very low shock when it's released. And the animation shows conceptually how it works. We send an electrical signal through.
So yeah, this is what I was talking about. Well, I was saying that they'll release the covering of the sun shield. So yeah, these are the actuators that they're going to use. So let's listen back in.
The split nut to separate, and then our pin can get extracted. And so in the case of the MRDs, it's a spring-loaded pin that pulls to release the folded membranes. In other places, we would be bolting two pieces of structure together and then releasing them so we can deploy them.
And the sun shield itself has 107 of these?
107 MRDs that all have to work.
Every single one
Every
has to work.
single one has to work. And 178 of this type of device in various configurations around the entire observatory.
Right. Well, if we go over here, we've got something sort of lovely waiting for us, a big gold hexagon. So tell us what we're looking at, a sort of a model here of a mirror segment, right?
Right.
Yeah.
Full-scale, single segment, one of the 18 mirror segments on James Webb. The real ones would be machined out of a single piece of beryllium to the exact curvature we need. And then once we're deployed on orbit, each segment can be individually focused to make it act as a single perfect mirror.
Now that coating, tell us about this gold coating here.
Yeah, so this is you know, coated with a very thin layer of gold. It's only a few hundred atoms thick of gold, and that gold is really good because it gives us a reflective property in the infrared, and that's really what Webb is an infrared telescope, and we need that sun shield exists to cool this entire telescope. So this mirror actually runs about -400 degrees Fahrenheit on orbit. If it were warmer than that, the infrared energy coming off of this, that heat energy would swamp our detector system and our instruments. So that entire sun shield exists to cool all 18 of these down. And again, this gold coating is what helps with all that reflectivity to make it perform even better.
Well, that's wonderful. So you put it all together, and we have a smaller mock-up here, the sun shield, the mirror. Tell us what we're looking at here.
Much smaller. So yeah, this is our entire observatory fully deployed on orbit. And you can see the sun shield here is a large feature. You can see all 5 layers that I talked about earlier. And it's the separation of those 5 layers which lets heat energy escape out to space before it eventually gets to this cold layer. Again, that entire telescope is running -400 degrees Fahrenheit, and the way we get it that cold is this side is shaded. The telescope is looking to the deep universe, which is near absolute zero. And then again, this layer here, we've got about a 500 degree temperature drop, so this telescope is also looking at this layer here, which is nice and cold. So that's what lets us, you know, harness thermal physics to cool this down to those really, really cold temperatures. Again, you can see our booms, which are fully deployed and stretching this out. and then ultimately all folds up and gets stowed into this structure for launch.
Right. So the membrane release devices would be along the back side of these structures on the forward and the aft side. And we release them in rows so that we can sequentially start to unfold the membrane once those pins are pulled out of the way.
Well, that's wonderful. Thank you so much for joining us, and best of luck on the launch. I'm very excited.
Yep, thank you.
Okay, let's get a live launch status update from NASA commentator Rob Navius at the launch site. Rob, how are things in Kourou?
Well, thank you, Michelle, and Merry Christmas from the Jupiter Control Center here in Kourou, French Guiana. You are looking live at an Ariane 5 rocket on its launch pad, ready to send the James Webb Space Telescope on the initial phase of its journey. The fueling of the Ariane 5's first and upper stages began before sunrise, and in the last few minutes, mission controllers here in Kourou and at the telescope's control center at the Space Telescope Science Institute in Baltimore conducted polls, with all positions reporting they are go to proceed into the final phase of the countdown. Launch controllers have been monitoring weather conditions throughout the night, keeping tabs on clouds and wind speeds, both at ground level and in the flight path of the Ariane 5, ensuring that all of the precise commit criteria are acceptable for launch. Right now, we have a green board, no issues as the countdown proceeds, no issues again being tracked by the flight control team here in Kourou. By the way, our broadcast today is a collaborative effort between NASA and the European Space Agency. So that's it from now. From the Ariane 5 Mission Control here in Kourou, we'll be back with you soon. For now, let's go back to the Goddard Space Flight Center and Michelle Fowler.
Thank you very much, Rob. So Webb asks big science questions. It demonstrates astounding technology. It inspires and excites people to dream and wonder. And the spark of inspiration is the ignition of creativity. Kids all over the world have a natural affinity for Webb's big pursuits. And now we have a collection of young artists ready to showcase their work.
Hi everyone, I'm Kelly Girardi, and this is Delta V, and we're kicking off the Unfold the Universe Challenge with NASA and the James Webb Space Telescope. NASA is hosting an Unfold the Universe Art Challenge. Use your imagination to share what you believe the Webb Telescope will find.
I believe that the Webb Telescope will see galaxies, stars, planets, the moon, and don't forget our star, the sun. Up in the sky, really high, it's space.
Ooh, space. Thanks, Greta. Good job.
This is my picture of space. Hello, my name is Gabriel. I am from Romania. This is how I imagine space. Hello everyone, good morning. This is the drawing of distant galaxies that can be seen by James Webb Space Telescope. Hi, my name is Anastasia, and this is what I drew when I think the telescope will look like, what the telescope will see. I drew the Earth, the Sun, a new planet, a black hole, and stars.
So we've been fielding social media questions from viewers all over the world this morning, and let's take a couple of minutes to share some responses. There's been a couple questions about how long will it take for images to come out, and there's a lot of things that need to happen before the images are coming. So Macarena, why don't you take us through some of that?
Yes, so for the first scientific beautiful images to share with the public, that will take 6 months. And the reason is because it is, so we launched today, it takes a month to take to the orbit place, to the Lagrange 2 point, and then we have a whole period of cooling down the instruments, aligning the mirrors, and making sure that all the instruments are ready to do science. So the whole process takes 6 months, half a year.
And also, all of those 18 segments of mirrors, something needs to happen to get them all working together too, right?
Exactly, because initially you launch with 18 segments and they work separately. So you will take, if you observe one star, you will get 18 little points. So there has to be a process where you take images with NIRCam, which is one of the cameras on board, start moving the mirrors slightly to make them work as a single one, and then by the end of this iterative process, you go from 18 points to a very sharp, pristine single point source. So all mirrors act as a single one.
So let's see, we have a question from LV coming in on Twitter. Will Webb be able to enhance detection of comets, asteroids, or meteors that enter our solar system? So that seems we've got a planetary person here.
Sure. Yeah, well, Webb does have a special observing mode where it's able to track these rapidly moving objects, because compared to these distant stars and galaxies, asteroids and comets, they move pretty quickly. And so Webb will be able to do this so that we can study material that's outgassing from them and learn more about what they're made of.
So let's see, there's so many good questions, so we only have time for a few more. So one is from Kristen Rodriguez on Facebook. How long will it take James Webb to reach Lagrange point 2? And you might also explain what is Lagrange point 2?
So it takes a month. I think it's actually 29 days to get there. And the Lagrange point is this very interesting stable point. So the gravitational pull between the sun and the Earth creates this point where it is stable, and you can, as you can see there, Webb can orbit around the L2 point in a very stable orbit, only needs a little bit of corrections once in a while, and it can always have the sun shield protecting the telescope from the radiation of the sun. In a year, in a full year, you can observe any object in the sky, and it's a continuous observation.
Well, thank you very much. We'll hopefully come back to a few more questions later.
Thank you.
So this is a big mission with a cast of thousands to bring it to life all over the world. As we get closer to launch, let's take a brief look at the main locations where Webb took shape on its journey to space.
Inside the massive high bay clean room at NASA's Goddard Space Flight Center, engineers assembled the 18 gold-covered mirror segments into the backplane of the telescope and integrated the 4 science instruments contributed by international partners. To simulate the harsh environment of launch, they went through vibration tests and acoustic tests. And to simulate a space environment, the instruments endured cryogenic testing in a large thermal vacuum chamber. But it wasn't large enough to hold both the instruments and the mirrors, so the telescope boarded a plane to Houston, Texas, to visit the only thermal vacuum chamber in the world big enough to fit the entire assembly. Chamber A at the Johnson Space Center was originally built to test the Apollo spacecraft, and half a century later, it provided a grueling 100-day test for the Webb Telescope. Next, the telescope traveled to Northrop Grumman's facilities in Redondo Beach, California to meet up with its other half, the Sunshield and spacecraft bus. Fully assembled at last, the entire observatory went through yet more tests. Many focused on making sure the spacecraft could properly fold up for launch and unfold in space. Then in September 2021, Webb caught a ride on a specialized cargo ship and set out on a 16-day voyage to the European Space Agency's spaceport in Kourou, French Guiana. According to its travel itinerary, that's Webb's last port of call on Earth.
Once Webb gets into space, we're going to have some exciting things to tell you about what happens next, from its extraordinary engineering to the thrilling scientific adventure it's about to enable us to undertake. But launch comes first. And for that, I'm going to turn it over to Katie Haswell, our host at the launch site, and one of NASA's most recognizable voices, launch commentator Rob Navis. It's all yours, Katie.
Thanks very much indeed, Michelle. Well, it's all looking very good here at the spaceport for a Christmas Day launch. Operations running smoothly, the countdown ticking over nicely. All the systems are green and we are go for launch. You can see there we're looking at launch pad number 3, the James Webb Space Telescope, inside the very top of the rocket in first class with its seatbelt on, waiting patiently for liftoff. That's scheduled in about 32 minutes' time. I'm in the Mission Control Center here at the spaceport, the nerve center of operations. We're about 10 kilometers from that pad, and behind me you can see it's a laser focus here in the control center with the mission control centers all on console there as we get closer to launch. We call this, there's a fishbowl behind this protected glass. And up in their skybox here in Mission Control are NASA's Rob Navius and the European Space Agency's Luce Fabregat, and they're standing by to take over the commentary about 15 minutes as we get closer to launch. First of all, though, let's check in on the countdown and let's see how things are progressing with Stefan Israel. Stefan is the CEO of Ariane Space. Ariane Space is the company responsible for getting our telescope into space today. Stefan, thanks for joining us. No pressure.
Good morning, Kathy.
How are things looking?
So we are now 31 minutes before liftoff. So far, so good. Ariane 5 is ready. Webb is ready, the range is ready, and the weather is green.
Well, that's good to hear. So what can we expect to see? What's going to happen?
Yes, so in the 30 coming minutes, we will make the final operations. 10 minutes before liftoff, we will have the final authorization of the weather. And 7 minutes before liftoff, we will enter in the famous synchronized sequence.
And, I mean, how's everyone feeling? I'm guessing everyone's...
We launched for humanity this morning from the Guiana Space Centre. You know what Webb is about? After Webb, we will never see the skies in quite the same way.
It's an important project, isn't it, for everybody?
It's a very special mission, but we have delivered already 111 times with Ariane. This is the 112th Ariane 5, so we will deliver this morning.
And everybody there in the control center, cool, calm, and collected. Stefan, thank you very much for having taken time to step out of the fishbowl for us, so you can head back now into the fishbowl and take up your position. Stefan Israel, thank you very much indeed. Stefan, of course, heads up what we call the flight desk, which is the authority that takes all the final decisions in the event of unplanned situations. Now, we are in French Guiana. We're on the northeastern coast of South America. We're in Amazonia. It's hot. It can get a little bit sweaty sometimes, and there are lots and lots of mosquitoes. But somebody who knows it very, very well is Raphael Chevrier. Raphael is a rocket scientist, or a rocket expert at least, from Ariane Space. Thanks for joining us, Raphael. Tell us a little bit more about French Guiana.
Well, French Guiana is a French territory that borders Brazil. It's located in the Amazon rainforest. 97% of the land is covered in trees, so that's why it's so green and beautiful. And you can totally imagine that the wildlife there is absolutely incredible. This is actually one of the best preserved habitats in the world.
And of course, it is in the jungle, and yet it is actually the European spaceport. So what makes this location in South America so important and so relevant?
Well, there are several reasons for this. First, we are on the coast. It means that we can launch over the sea from north to east without having to fly over inhabited area. So this is very convenient to reach any kind of orbit. There is no hurricane here, big tropical storm, there is no earthquake, but more importantly, we are very close to the equator, so that we can benefit from what we call the slingshot effect given by the rotation of the Earth. So let me take this globe. Basically, here on the equator, we are all traveling at roughly 1,000 miles per hour. That's very convenient. Of course, we don't feel it. If we were on the poles, that speed would be very, very close to zero. It means that when Webb is right now on the launch pad, inside the fairing of the Ariane 5, it's already traveling in the right direction, and we can use this extra boost to get us into space. That's also very convenient for Webb, because doing so, it can save its fuel and increase its operational life in orbit at 1.5 million kilometers from here.
And that really is important, 1 million miles, isn't it? And so there's a real proper slingshot effect. Yeah. And the facilities here are ultra high-tech, and that's exactly what Webb needs, isn't it?
Yeah, that's very convenient for Webb. It's also located in a nature reserve. So this is the perfect meeting between nature and technology, and people come from all over the world to work here. But one thing that's been very important for Webb is cleanliness, because you know that one speck of dust could alter the vision of the observatory in space. That's why we have been extremely careful in keeping a pristine environment in all our facilities, from Webb's arrival in French Guiana to sealing it inside the rocket.
So let's talk a little bit now about the Webb Space Telescope. I really don't think you need me to tell you that it is the product of a feat of human ingenuity. And you don't get to make a telescope as complex as the James Webb Telescope and as remarkable without tremendous amount of collaboration. And the James Webb Space Telescope is indeed the product of a partnership between 3 space agencies who came together to create it, NASA, the European Space Agency, and also the Canadian Space Agency. So here to talk about that now is Greg Robinson from NASA. Greg, thank you very much for coming to the floor, out of the fishbowl as well for us. And we're talking serious teamwork here, aren't we?
Yes, Katie. We've benefited from an amazing partnership with the Canadian Space Agency and the European Space Agency. Over the life of the development, we've had more than 10,000 people actually touch Webb, 29 states in the U.S. and 14 countries across the globe, and not to mention the amazing industrial base across the globe that have benefited here. In order to do bold missions like this, it takes lots of resources and lots of expertise, so we maximize everyone's expertise.
And how did this bold mission get onto an Ariane 5 European launcher?
So as part of the partnership, the Canadian Space Agency contributed science instruments, and they're incredibly important for this mission. And so did ESA, science instruments, and the amazing Ariane 5 that we will see take us on this journey and put us in the right direction to get to Lagrange Point 2. And we're looking forward to that.
It's a tremendous atmosphere here, isn't it, in the Mission Control Center? There's a real buzz here today. I wonder how you must be feeling, Greg. I mean, it's got to be a very, very emotional time knowing that your telescope is sitting there on top of the rocket getting closer to launch.
It's certainly amazing. I often talk about the butterflies, and people keep asking me, have they started? Have they started? And yes, they're starting. And when we get to about
collected. Thank you, Greg Robinson. You can take your position back in the fishbowl now because I know you've got a lot of work to do in there. Greg Robinson, thank you very much indeed for joining us. So the Ariane 5 launch vehicle is the heaviest lifter in the Ariane 5 Ariane family of launchers. And Raphael, she has got an incredible track record, hasn't she, of success?
Yeah, this is a very reliable and successful rocket.
Webb Telescope right at the top, inside the fairing.
It is right there on the launch pad, and together they are put on top of the third stage, a cryogenic stage, and it is this upper stage that is going to place Webb into orbit.
And what about the engines? What are we going to see at liftoff?
At liftoff, we first see the main Vulcan engine ignite first. We do this because we want to check it's working properly before we switch on the solid boosters 7 seconds later. Once it's done, there is no turning back. The rocket is going to liftoff. And so, yeah, that's very, don't be surprised. Don't be surprised if you don't see the rocket lifting off for 7 seconds. that's time for the rocket to actually warm up before soaring into the sky.
So once we light the touch paper, you can count to 7 before it actually lifts off. Now, one of the advantages of the Ariane 5 vehicle is that it can be modified, and that's exactly what we've done for today's launch. We've had to make some changes for it to be able to host the Webb satellite. And joining me to talk about that is somebody who, the right person for the job indeed, because he was in charge of those changes, Daniel de Chambre from the European Space Agency. Thanks for joining us, Daniel. What did you have to do?
First, we need to recall that Webb will be the largest payload to be ever accommodated on Ariane 5. It fully occupies the volume of the fairing, with gaps as small as 10 centimeters for a diameter of 5 meters. It is the reason why we had to develop a specific integration procedure to ensure that there is no contact with them. After separation, during separation, the venting system of the launcher has been improved in order to balance as much as possible the inside and the outside pressure of the fairing. And this is due to the fear of a depressurization shock, which could damage the delicate layers of Webb submerged shield. After separation, due to the fact that some equipment of Webb are very sensitive to sun exposure, the roll control of the launcher will be tuned in order to make sure that Webb is always oriented only one face to the sun. And in addition, to avoid any hotspots, the launcher will create some oscillating movements, like a barbecue mode, to avoid any overheating. And after Webb separation, there will be a specific end-of-life maneuver to be applied on the upper stage in order to put it on a liberation orbit around the sun in order to avoid collision in the long term.
Thank you very much indeed, Daniel. So we'll hopefully see the upper stage rocking in space. Not quite all the way around like the familiar barbecue, but a slightly different movement. Listen, gentlemen, thank you very much indeed for being with us today. I know that you're busy. You've got jobs to do inside the fishbowl, so I'm going to send you right back there now, and very best wishes for the launch. Thank you.
Thank you.
Our telescope has a long journey ahead of it. It's got to travel 1 million miles to its destination in space, its working zone, where it's going to start telling us all about our universe. It's already started that journey because it's traveled to the launch pad from Los Angeles. After final tests were concluded in Los Angeles, Webb was packed into a special container and transported along the LA 405 freeway, which had to be closed because it's so big. It traveled on a special ship. A lot of spacecraft will come to the French Guiana launch site by plane, but Webb was too big for that, so it had to travel by ship, and it went through the Panama Canal. Up through the locks. And it took 16 days to get to the port in Kourou, where it was unloaded and traveled to the spaceport. That's not the real Ariane 5, that's a model, just outside the Jupiter Control Center, actually. It was unpacked very carefully in the facilities that Raphael was talking about. And then fueling started, and of course, the teams had to wear special suits because that's a dangerous job. And then it was placed all the way on top of the Ariane 5 rocket. It was encapsulated inside the fairing and sealed, and then it was rolled out to the launch pad 2 days ago. from the vehicle assembly building to the pad along very special rails. Very, very slowly through the Amazon rainforest. It was raining at the time, and that was 2 days ago, and here we are now, 17 minutes and 46 seconds to launch and counting. All systems are go here at the European Spaceport in French Guiana. We have 3 control centers on the job today. We have the Mission Control Center here. We also have the Launch Control Center, which is about a mile from the pad. And then we also have the Telescope Control Center, Mission Control in Baltimore in the US, and that's where the operational teams are standing by to take over the telescope operations. Once it's released from the mothership, that will be about 27 minutes after launch. And they'll be controlling the Webb Telescope for the rest of its life. Very important job. The James Webb Space Telescope is a truly remarkable observatory. People have been working on it for over 2 decades. Some people have been working on it for their whole professional lives. Thomas Zurbuchen is the head of science at NASA, and he's joining me now just to talk about it. Thomas, or Dr. Z, as we can also call you. The day has come. All these decades, all this time, all these people working on the telescope, and here we are, 16 minutes and counting to launch. It's a big day, huh?
Oh, I'm so amazed, right? We have this telescope on top of this rocket, a telescope that 10,000 plus people have worked on in many ways, and together with that telescope, all the hopes and dreams of those individuals, and also tens of thousands of scientists, some of them not even born, that will benefit from these data, are there with them waiting for these last minutes of countdown for its journey to space.
I'm guessing people are feeling a combination of emotional excitement. What's going through people's minds, do you think?
Oh, I think there's a tremendous sense of accomplishment. Whenever you're on top of a rocket, many things went really, really well. There's tremendous pride. There's always a little bit of anxiety. We know launching is hard. We have one of the absolute best teams in the world working on this right now, so I'm confident in that. We're super excited. It's just an amazing day today.
And what are you most excited about, Dr. Z?
Well, I'm a scientist, so for me, besides the technology that really is a marvel, it's really the best we can do. What I'm thinking about is really looking at the universe in new light. We have never seen the universe how Webb will show it to us. And can you just imagine going back in time, 13.5 billion years? It boggles your mind, even as a professional astrophysicist. Kind of just think about all the new things we're going to learn about our most beautiful universe.
Dr. Z, thank you very, very much for joining us. And I want to wish you and all the teams, everybody, the very best for today's launch. Thank you.
Go Webb.
So, yes, indeed, go Webb. So we are now 14 minutes and 30 seconds to launch. We're getting really close now. Everything's going well. All systems are green for launch. And I'm going to hand you over now to NASA's Rob Navius in the skybox alongside the European Space Agency's Luce Fabrichet, who are going to take on the commentary from here on in. Over to you guys. Rob.
Well, thank you, Katie. Merry Christmas to our worldwide audience from our broadcast booth high atop the Jupiter Control Center here in Kourou. Joining me today for this historic launch, my colleague Luce Fabrichet, the head of infrastructure and value chain for the European Space Agency. Luce, good morning.
Good morning,
with you. Great to be with you today.
Very pleased to be here with you and all of you watching us for this very special event.
Well, at this hour, countdown clocks are ticking backward. We are at T-minus 13 minutes, 32 seconds and counting. Out on the launch pad, everything is in great shape. Don't let those clouds fool you. We are go for launch. The latest weather briefing just completed indicated that all weather parameters are green. We have a green board here in the control center, and everything has gone extremely smoothly in the countdown. About 9 minutes ago, a major milestone passed as the James Webb Space Telescope began the process and completed the process of receiving commands to transition from external power to internal battery power following the latest in the series of those weather briefings. Webb will remain on internal battery power until its singular solar array unfurls about 30 minutes after launch. Earlier, telescope controllers reported good environmental readings from sensors inside the fairing encapsulating the telescope atop the upper stage of the Ariane 5 rocket. And Luce, as we enter the most critical phase of the countdown, can you outline some of the upcoming critical activities as we head into the phase called synchronized sequence?
Yes, Rob. We are now reaching the end of this 11-hour sequence that we call the chronology, and that started yesterday evening. All systems here have been prepared for final launch operations. And at the time being, it's rather quiet now inside the launch table and also inside the launcher. We were told a few minutes ago by the Launch Control Center here that the launcher fluids and electric systems are ready for the final automated sequence. They are on hold now, waiting for the last weather report at minus 10 minutes. After this weather report, 3 minutes later, we will have the beginning of this famous synchronized sequence when all systems will be made ready for the liftoff. This sequence will first be run by the ground calculator, and then the onboard computer will take the lead step by step, and the launch vehicle will be made autonomous from the ground system. You know that we have 2 tanks in each cryogenic stage, upper stage and main stage. All 4 tanks are, of course, thermally insulated from the hot environment we have here in French Guiana. However, these liquid propellants are at very low temperature, and because of that, slightly evaporate. And to ensure they are perfectly loaded at liftoff, their final loading and topping up will last up to 4 minutes before the launch. So that will be the beginning of the synchronized sequence run by the ground calculators. Then we will have on the fluid side the end of the topping up, the final loading and the topping up of the different tanks. And on the electric side, we will have the onboard computer getting prepared for the launch also, and it will be uploaded with the H0, time, the time for the liftoff, which is today at the beginning of the window, 9:20 local time, 7:20 Eastern time.
And Luce, we're coming up on that final weather report. We expect all systems to remain green. We'll be going down to the fishbowl to confirm that just a moment or two from now. It's a 27-minute ride to orbit from liftoff until the time that the Webb Observatory is separated from the upper stage of the Ariane 5 rocket. Several minutes later, the commands will be given to unfurl its solar array, followed by the confirmation from the telescope controllers in Baltimore that we are power positive, meaning that electrical current is flowing through that solar array. With us today inside the so-called fishbowl, seated with mission controllers on the floor of the control room, is Raphael Chevrier of Ariane Space. Raphael, how's everything looking? What's being discussed down there?
Hi, Rob. Well, so far so good. We just received the last weather forecast. It's all green for the H0 that is forecast right now. What we checked was altitude winds in the vicinity of the launch pad, and risk of lightning. So right now, it's a relief because the weather was a bit tough in the last couple of days. But right now, everybody is very focused on the next steps. The start of the synchronized sequence at 7 minutes before liftoff. Last operations that Luce described earlier before Webb and the Ariane 5 are going to lift off and soar into the sky.
Thanks, Raphael. We'll be back with you and Luce here shortly. We now have confirmation from Baltimore that James Webb is on internal power. Amidst all of this activity, we cannot forget that it is Christmas Day. 53 years ago, the astronauts of Apollo 8 completed their 10th and final orbit of the moon after reading from the book of Genesis on Christmas Eve to billions of people watching with rapt attention back on our planet. The astronauts then headed for home following their spacecraft's trans-Earth injection burn. Today, more than a half-century later, we're just minutes away from another Genesis, the genesis of new era of discovery. The launch of the James Webb Space Telescope is at hand. We're just 38 seconds away from entering the critical synchronized sequence. You're going to be hearing all the critical calls from the DDO, the Range Operations Manager, who is Jean-Luc Voyer, here in the in the Mission Control Center. There he is. He will be calling the start of synchronized sequence, all of the critical countdown milestones, and we will be listening very intently for his calls. Let's stand by.
À tous le DDO, attention pour la séquence finale lanceur. Top à 0-7 minutes.
And with that, we've entered the period of synchronized sequence. You heard Luce Fabregat just a moment or two ago explain some of the critical activities, the first one coming up just a few seconds from now, which will be the topping off of the main stage tanks. The first or core stage was loaded earlier this morning with 175 tons of propellant, 150 tons of liquid oxygen, and 25 tons of liquid hydrogen. The upper stage loaded with 15 tons of propellant. That will be the workhorse for a 16-minute burn to lift James Webb to its final orbit. At separation, some 27 minutes and 7 seconds after launch, James Webb will be at an altitude of about 864 statute miles. To put that into perspective, some 520 miles higher than the Hubble Space Telescope and more than 600 miles higher than the International Space Station. Webb at that point will be traveling about 21,000 miles an hour as it heads out to a highly elliptical, halo-like racetrack orbit some 1 million miles from Earth to begin its scientific observations.
In a little more than 1 minute from now, we will see the 4 tanks pressurized at their flight level for the last test before the ignition of the Vulcan engine. And in parallel, the electric system are also set in flight configuration, the onboard computer. The electrical power, as for the telescope, it will switch from ground to internal power 1 minute before the launch, 1 minute and 5 seconds before the launch. And we are going to see -6 seconds. At -6 seconds, we will see the disconnection of the upper stage, these big cryotechnic arms you can see on this picture. Then, 3 seconds before the H0, the inertial platform that will give all the information about where it is to the launcher will be released. And at H0, the 7-second sequence to ignite the Vulcan engine of the main stage will start. That will take 7 seconds, a little less than 7 seconds, where the engine will start up to its flight regime. Once the computer has checked that the Vulcan engine is running normally, and you will see at that point a flame going stable at the outlet of the nozzle, and at that point the onboard computer will ignite the 2 boosters that will enable to move the 770 tons of Ariane and Webb.
Coming up on the T-minus 4 minute mark right now, just a couple of milestones real quick. At the 1 minute 5 second mark into the flight, Ariane 5 will go through the period of maximum dynamic pressure, max-Q as it's known. That will be the period of maximum aerodynamic forces on the rocket itself. The solid rocket boosters, which will provide about 90% of the initial thrust off the launch pad, will shut down and separate at the 2 minute 21 second mark into the flight, followed 1 minute and 5 seconds after that by fairing jettison. That will expose the James Webb Space Telescope to the environment of flight for the first time. The main stage separation, or the first stage separation, comes at the at the 8 minute 47 second mark into the flight, and that will be about a 16-minute burn of that upper stage engine. It will cut off at about 24 minutes, 51 seconds into the flight, and then we'll go into a coast phase of about 2.5 minutes to allow any oscillations to dampen out, provide the most pristine environment for the James Webb Telescope before observatory separation. We're coming up on the 2-minute, 50-second mark into the flight. Again, you're going to be hearing critical calls down the stretch here from the DDO, or the Range Operations Manager, Jean-Luc Voyer. The weather is go. We have a green board, no issues being worked. NASA officials, including Greg Robinson on the right, carefully watching the telemetry, looking intently at the final couple of minutes of the countdown. Lives have been spent in the preparation of the James Webb Space Telescope that is about to fly.
As we get into this, and it's getting quite exciting here, and I mean, it's just.
And that is the DDO, the Range Operations Manager, Jean-Luc Voyer, as we have hit the 2-minute mark in the countdown.
Excuse me?
The flight will be in 2 phases. You will see the first part of the flight during the solid rocket boosters phase. That will be the atmospheric part of the flight, the atmospheric flight, and the trajectory will be driven by a to reduce the aerodynamic loads, and we will have a very different exo-atmospheric flight after that.
And you were watching a number of people, VIPs and invited guests, moving out to the observation platform that is right next to the Jupiter Control Center as we stand by for the 1-minute call from Jean-Luc Voyer.
À tous les DDO, attention pour moins 1 minute. Stop, à 0 moins 1 minute.
Thumbs up from Jean-Luc Voyer.
Yeah, there's 1 minute mark coming up now. And, well, 52, 51.
The Vulcan 2 engine will ignite. Turbo pumps will come up to flight speed for 7 seconds, and the command will be issued to ignite the solid rocket boosters. The James.
There's a second time gap here where the ignition first gets of the Vulcan engine, the Center engine, and then turbo pumps up and solid rocket booster ignite on the command, and it's set free. So yeah, that's how it's gone. It's branded very nicely, the fittings.
À tous les DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest to the edge of time itself.
Yay!
James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight. Good pitch program reported.
Trajectoire nominal.
Vehicle performance is nominal. The Ariane 5 rocket continues to fly uphill in nominal fashion. The rumble of the powerful Ariane 5 now being felt here in the control center. 3D animation.
We can hear the noise and feel the vibrations here. You're right, Rob. Yeah, impressive.
13 kilometers in altitude, 7 kilometers downrange, traveling about 0.6 kilometers per second.
Les paramètres à bord sont normaux.
The trajectory reported to be nominal by Jean-Luc Voyer, the Range Operations Manager. You can see at the bottom of your screen, the yellow line is the trajectory plot, perfectly overlaid over the green line, which was the pre-launch trajectory.
Okay, so yeah.
1 minute, 41 seconds into the flight, about 40 seconds away from shutdown of the solid rocket boosters. coming up on the 2-minute mark into the flight.
When it detects the threshold on acceleration, not the deceleration, but less acceleration.
Tous les paramètres à bord sont normaux.
Everything is okay. Everything is normal.
2 minutes, 15 seconds into the flight.
When the computer detects this threshold, it will separate.
Okay, so yeah.
Séparation des EAP.
Done.
We have confirmation of solid rocket booster separation from Jean-Luc Voyer. This coming at an altitude of 44 miles. The Ariane 5 and James Webb traveling almost 5,000 miles an hour. We have about 1 minute, 5 seconds to go before fairing jettison. That'll be the next critical milestone.
The fairing is there to avoid the satellite being exposed to high temperatures and also high airflows. And as soon as the launcher leaves the atmosphere, as is now the case, the satellite does not need anymore to be protected, and Webb does not need anymore to be protected. So each kilogram being very important for the performance of the launch, we are going to eject this no more useful fairing.
And let's go down to the floor in the Jupiter Control Center to Raphael Chevrier of Arianespace. Raphael, so far so good.
Hi, Rob. So far so good. Everything is nominal, as we say when asked.
So as she said, that the fairings protected and fairings protect the so yeah, as she said, the fairing protects the satellite from any sort of harm from the heating from the atmosphere, but as soon as we reach a height, all of this stops, which means we can lose any sort of extra kilograms from the rocket, and that's why these fairings have been deployed. Citizens.
There's your telescope, ready to unfurl its wings, basically, and begin its journey to the Lagrange point, the L2 point, about 1 million miles away from Earth.
La trajectoire est nominale.
Trajectory is nominal. The report from Jean-Luc Voyer. The liftoff time confirmed here in the Mission Control Center at 12:20 Greenwich Mean Time, 9:20 a.m. Peru time, 7:20 a.m. Eastern Time. The Ariane 5 and James Webb, 181 kilometers in altitude, 450 kilometers downrange from the launch site here in Kourou.
Flight control is very smooth.
5 minutes, 12 seconds into the flight. We have about 3.5 minutes to go in main stage or first stage performance. And again, you can see at the bottom of your screen the yellow plot line overlaid over the green line, meaning we are right on course, right down the pike, and a perfect trajectory so far for the Ariane 5 rocket.
Les paramètres à bord sont normaux.
All telemetry data are now received by the Galileo tracking station, which is close to here, where we are in Kourou. It will track the launcher up to the ignition of its upper stage.
L'étage est calme, la propulsion est nominale.
And then we'll have the natal station in Brazil, Ascension as you can see on the map, in the middle of the ocean, and the two last stations in Africa, Libreville and Malindi, one on the east coast, the other one on the west coast. And the one on the west coast, Malindi, you can see that the telescope will be separated more or less over this Malindi station. And this Malindi station will also acquire the telemetry data from the telescope. You can see both are green, Galileo and Natal on this animation. It means they are expected to receive the data, and it was confirmed right now by the launch operations manager.
Acquisition de télémesure par la station de Natal au Brésil.
And just confirming now that telemetry is being processed through the Brazilian tracking station. The telescope is also processing telemetry through the tracking and data relay satellite system. As it moves further and further out into deep space, all of the telescope's telemetry and its imagery ultimately will be processed through the Deep Space Network in Goldstone, California. We passed the 7-minute mark into the flight. A perfect ride so far on the Ariane 5. We have about 1.5 minutes to go in the first stage performance. Once the main stage engine is commanded to cut off, it will be jettisoned, and just a few seconds after that, the upper stage engine will ignite, and it will be the workhorse for a 16-minute burn that will put James Webb into its preliminary orbit. About 11 minutes from now, telescope controllers at the Space Telescope Science Institute will be sending commands to prepare James Webb for the initial series of commissioning activities that will lead to the deployment of its solar array and the initiation of generation of electrical power for the telescope. About 30 seconds away from main engine cutoff.
La trajectoire est normale.
Nominal trajectory continues to be the watchword for the day from the Range Operations Manager, Jean-Luc Voyer, as we stand by for main engine shutdown and separation.
Extinction de l'EPC. Préparation EPC.
And we have main stage shutdown and separation confirmed here in the Mission Control Center, and the ignition of that upper stage. And Raphael Chevrier down in the fishbowl. So far, so good.
Yes, Rob, we have the confirmation of the separation of the main stage and the ignition of the upper stage. The trajectory is perfectly nominal. This is a very important moment for us because it's always a challenge to switch on a cryogenic engine in space condition, and we are now at 220 kilometers of altitude. Speed is a bit more than 7 kilometers per second. As we enter now the second stage of the second phase of the flight, the upper stage is going to power for about 16 minutes to place Webb on its transfer orbit, and right now everything is again nominal as the DDO just said.
And a short time from now, the so-called sawtooth maneuver will get underway. Again, like rocking a baby in a cradle, this will be a maneuver to keep Webb's optics protected from overheating loose.
Exactly, Rob, like a baby in a cradle. You can see here Webb attached on top of Ariane 5 upper stage with a very specific configuration. Of course, it will be different during its lifetime, but for the time being, its sun shield is folded and not yet fully protecting the observatory. A number of studies have been performed by the mission teams in Europe, in the US, on the thermal conditioning inside the telescope and the way the rays of the sun would propagate and interact with sensitive equipment inside the telescope. Maintain this thermal conditioning is really key before separating this telescope. And in particular, we know that one face of the telescope cannot face the sun. That's why and to produce these right thermal conditions inside Webb, a specific roll law has been designed, what we call the sawtooth approach. And if you are watching carefully to these images, you can see this animation. You can see that the upper stage is going 30 degrees on one side, then 30 degrees on the other side, going back and forth this way to maintain this perfect thermal conditioning for the telescope.
It's worthwhile noting that after Webb separates from the upper stage of the Ariane 5 rocket, which continues to perform in excellent fashion coming up on the 12 minutes. of the mirror's segments. All 6 reaction wheels and the wheel drive electronics will be powered on for Webb, and that will be the precursor to the attitude control system using those reaction wheels to maintain the proper orientation with the sun, as opposed to using onboard thrusters. Of course, fuel in those thrusters, very valuable. It's a limited commodity for the lifetime of James Webb's observations of the universe. We're 13 minutes, 55 seconds into the flight. Jean-Luc Boyer, the range operations manager, continues to report a nominal performance for James Webb. And again, Luce Fabregat from the European Space Agency, how is this trajectory being carefully and methodically adjusted to provide the correct parameters in the final stages of ascent?
Yes, Rob, as you can see on this plot, the altitude is slightly going down. It's perfectly normal. The launch vehicle is really on the line where it should be. This decrease of its altitude, slight decrease of its altitude, will allow the launcher to benefit and the upper stage to benefit of the gravity effect, and to increase its velocity until it reaches a thermal threshold. It's about to reach it, or even already reached it now, and it will go up. And now it will go up and up to the separation of the Webb telescope. It will separate the Webb telescope on a highly elliptic orbit, but still around the Earth. The telescope will be released, inserted on an orbit around the Earth, with an apogee, a very high apogee above 1 million kilometers.
Trajectory nominal, as reported by Jean-Luc Boyer. You see him in that view, 185 kilometers in altitude, some 4,500 kilometers downrange from the launch site here in Kourou, moving at more than 8 kilometers per second, right on the plot, right on the trajectory, everything looking great. We are about 9 minutes away from the completion of upper stage ignition. It's shut down, and then about a 2.5-minute coast phase before Webb will separate. Observatory separation will be called out. You'll be hearing those calls and the initial calls from Carl Starr, the mission operations manager at the Space Telescope Science Institute at Johns Hopkins, through solar array deploy and the declaration of a power-positive spacecraft. James Webb, of course, will be traveling well beyond the moon to a distance of about 1 million miles away from Earth, settling into a highly elliptical, halo-like orbit to begin its astronomical observations. And again, as we mentioned earlier, at the time of observatory separation, Webb will be at an altitude of approximately 864 miles, statute miles, traveling some 21,000 miles an hour. We're about 8 minutes away from upper stage shutdown. The stage has performed as planned. No issues reported. The launch occurring at 12:20 Greenwich Mean Time, 9:20 Kourou time, 7:20 a.m. Eastern Time on this Christmas Day.
Very smooth. The velocity you just mentioned is very important, Rob. The velocity you just mentioned, the separation of the telescope, is very important. It will be slightly below, okay, I give it in a kilometer per second, but it will be slightly below 10 kilometers per second, because it's important that the satellite, the telescope, is not inserted on an escape orbit. It will be placed on a terrestrial orbit so that there will be time for the layout, for early stage operations and the commissioning of the telescope. And that will be, in fact, the upper stage that will leave this orbit and goes toward an escape or liberation orbit.
And of course, even though we're still in powered flight, the trajectory, the acceleration, the speed at which James Webb is going towards its preliminary orbit, all modeled in advance and carefully choreographed to maintain as quiescent an atmosphere and environment around the telescope for its ultimate separation from the upper stage of the Ariane 5 rocket, which is about 6.5 minutes from now. 18.5 minutes into the flight. It's very quiet now here in the control center here in Kourou. NASA officials, European Space Agency officials, Ariane Space officials, all watching telemetry very carefully. And as the upper stage continues to burn nominally and sheds fuel, the acceleration uphill for the James Webb Space Telescope continues to increase as we approach the 20-minute mark into the flight. Again, upper stage cutoff is scheduled at the 24-minute, 51-second mark into the flight, about 5.5 minutes from now.
After the cutoff of this main engine, as you said, Rob, we will have a short ballistic phase, a short coasting phase that will, when the upper stage will rely fully on its what we call the attitude and roll control system, and it will adjust its attitude so that during this small ballistic phase, all the requirements from the telescope are fully met. And that at the separation, when there will be the separation, the conditions will be very smooth and as requested for the telescope.
Le pilotage est calme, la propulsion est nominale.
Today's countdown was as flawless as you can imagine. The weather was perfect all the way through the early morning hours, through the fueling process of the vehicle. The weather's been a bit dicey here in Kourou over the past few days, but everything fell together on this Christmas day to send a new present to the world's astronomer. 20 minutes, 40 seconds into the flight.
Trajectoire est normale, tous les paramètres à bord sont normaux.
All parameters nominal as reported by Jean-Luc Voyer, the range operations manager. 4 minutes of powered flight remaining.
The telemetry of the launch vehicle is acquired for the time being by the Libreville tracking station on the western coast of Africa. Flight control is nominal. The trajectory is fully normal, fully as expected, as you can see on the plot with the yellow plot over the green one. That is the expected one.
22 minutes into the flight. Less than 3 minutes of powered flight remaining.
Pilotage est calme.
Smooth flight control.
And again, as we've mentioned before,
les paramètres à bord sont normaux.
Everything nominal reported by the range operations manager. As we've mentioned before, this is a long ride uphill for the James Webb Space Telescope to put it at the proper position in the sky so that it can escape from the Earth, basically head beyond the moon towards its final orbit for its commissioning activities that will be the dominant feature of all of the operations from the Space Telescope Science Institute over the course of the next several weeks.
And the launch operations manager announced the acquisition by the Malindi station, as expected, for the end of the flight and the last part of the upper stage flight and the separation of the telescope.
James Webb is about 4 minutes away from separating from the upper stage. And again, at that point, it will be on its own. And again, those milestones that we discussed a bit earlier in the broadcast will begin to be followed carefully by the telescope controllers at the Mission Operations Center, the MOC as it's called, at the Space Telescope Science Institute in Baltimore. 1 minute of powered flight remaining. The upper stage continues to function perfectly. It's been a smooth ride for the James Webb Space Telescope.
Trajectoire nominale.
That upper stage was loaded pre-flight this morning with 15 tons of propellant for this long 16-minute burn. Now about 30 seconds away from upper stage cutoff. And we're standing by for upper stage shutdown and the cutoff of the upper stage engine.
Yay! So that's the confirmation that upper stage has cut down.
ESA.
And we'll be waiting for the last.
Tous les paramètres à bord sont normaux.
The extinction of the shut-off of the cut-off of the engine was confirmed exactly as expected, with the exactly expected altitude and speed and velocity. So now we have entered the coasting phase, the ballistic phase, that will last for a little more than 2 minutes.
And the telescope controllers in Baltimore confirming that all of the function parameters for the James Webb Space Telescope have been loaded on board the telescope. We are expecting Webb separation at the 27-minute 7-second mark here into the flight. Just over a minute from now, springs will gently push Webb away from the upper stage of the Ariane 5. As it moves further and further away from the upper stage, there'll be what we refer to as a collision avoidance maneuver.
Yes, Rob, exactly. The springs already will give some distancing, of course, between the two objects, between the telescope and the upper stage. And then the upper stage will leave the trajectory of the telescope and make a special maneuver to pass the telescope and head towards a liberation orbit and leave the telescope on its orbit without any risk of collision and without any risk of pollution towards the telescope.
And we're about 17 seconds away from Webb separation.
10, 9, 8, 7, 6, 5, 4. Yeah, 3, 2, 1. And yeah, that's the confirmation.
Séparation Webb Space Telescope. Go Webb!
Yay!
We do have confirmation of observatory separation. The James Webb Space Telescope,
and that's finally
here in the Mission
it has
Control
been
Center,
released.
Now taking its first steps in pursuit of cosmological discovery. It was a perfect ride to orbit. And all of the separation sequence of in good fashion according to the telescope controllers. And there is the view from the upper stage cap on the Ariane 5 looking at the James Webb Space Telescope as it moves gently away from its launch vehicle.
Space Telescope.
Go Webb, go Webb.
Yes, go Webb.
Well,
ironically enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth.
Yes, you're right, Rob. Impressive, fantastic pictures. Yeah.
Now we'll be hearing shortly from the Mission Operations Manager at the Space Telescope Science Institute, Carl Starr, who will be calling out the procedures that will lead to the deployment of Webb's solar array. And down in the fishbowl where there is jubilation, let's go to Raphael Chevrier of Ariane Space. And before we do that, Raphael, a bit earlier than planned, but there is the solar array having been deployed.
Yay! That's
Webb now has its array out as we stand by for confirmation that it is power positive.
Hey, Rob.
Okay, so.
J'entends pas si Rob. Il m'a appelé ou pas? Il m'a appelé ou pas, Rob? Non.
Well, that's it for today, guys. A successful launch, a successful deployment, successful staging, and a final successful deployment of the solar arrays. And well, that's it for today. Well, we'd quickly like to thank our patron, Ben Sanford, for all his patronage over the months from June till now, and he's been supporting us to run this channel. Well, thank you, Ben Sanford, and we hope to see you soon back. Well, he's not been pretty much available these times. Maybe it's due to the timings. Well, anyways, see you ahead, and bye, guys.